Yeah, so actually, when I first started this, Ed, you're actually one of the first people that I had in mind for the podcast when I first started going out.
Thank you.
You, Madalena, Seth, Flaxman, for example, several other people, less in the statistics and more in the engineering profession. And the reason I had you particular guys in mind was that because you gave such great presentations, and so like the clarity of it. I remember the first presentation that I saw you speak at. Funny enough, I think it was actually the first time I actually also saw Cynthia Rudin speak. It was actually in the same session. And I just thought that, like, because the clarity and the effort that you guys put in, I just thought it's like, if we could just have conferences of only presentations of that quality, one, we could have fewer conferences, and two, like they would I would have to go to every conference because they were of high quality. And I think that was back in, I would say like 2016, I think.
That sounds probably about right. Yeah.
Yeah. I feel like we were going like real hot and heavy in 2016 conference season. And then unfortunately 2017 hit and I had to write up. And so basically then I only knew the insects that crawled under my rock. And so, but yeah, no, I'm really excited. And it is of course strange to have you on. We've been going for about a year now, but yeah, you were one of the people I originally had in mind because I liked your presentation so much and just thought we need to deliver more Ed to the people. So
I appreciate that.
Yeah. So
I mean, there should always be a proper, proper amount. Like, too much Ed can be a problem, but I think a little bit wouldn't hurt anybody.
Yeah, a little bit here and there.
Ed in your life.
Yeah, but I think. So I guess we intersect on a few things. One, we're both people who've put a crap ton of effort into, like, for example, presenting well, so that people really got what we're doing. There's also obviously the cognitive bias that we both work in anomaly detection. Yeah. And where I work in, I would say more of traditional anomaly detection, so anomalous observation detection. And I guess I think that you are much more solidly in anomalous pattern detection than I'm in. I'm more like anomalous observations and anomalous time series, whereas you actually, it's more pattern based.
Yeah, pattern is a very big piece for us. Yeah.
Yeah. So maybe that's a good place to start. What is the difference in your mind between anomaly detection, for example, the one-off observations versus anomalous patterns? Because your bit seems tougher.
Yeah, no, let me try to, so this is my kind of view I developed over, maybe the last decade or so. And so actually, when I talk to my students about this, I teach an exploratory analytics class. And I have a whole module on anomaly detection because it's my favorite topic. So I enjoy it. It's my favorite section to talk about. And I think so many questions that we care about in science end up coming down to questions of anomaly detection. And so I have kind of a theory on or the framework for how I think about these things. So first thing I do is I distinguish between outliers and anomalies kind of personally. And again, this is not sort of agreed upon by the community. It's sort of my viewpoint, but I think of outliers and anomalies sort of being the same thing and not sort of when you see them, but really trying to better understand or differentiator being what produced them. So I think about like an outlier and anomaly both as extreme or abnormal outputs or outcomes. But with an outlier, let me use an example. So like, let's say fraud detection, very canonical example for anomaly outlier detection. Glenn, you're using your credit card over and over and over again, producing transactions. And so you are a data generating process. You are distribution, for lack of a better word. And I can observe a bunch of data drawn from the Glenn distribution on his, let's say, Visa. And every now and then you will make a purchase, right? I'll see an observation if I'm Visa that's a little abnormal or maybe extremely abnormal, depending on kind of what's going on in your life at that point. And that making it rain. Exactly. Yeah. COVID, you get saved all that money up from COVID. So now,
now time to spend. Yeah.
Just spend, right? Mm-hmm. And so those are outliers because the process that generated it was still the proper distribution, still Glenn, but it was extreme and maybe statistically speaking was a little bit odd. Whereas if someone stole your credit card and made a transaction, well, then that is an anomaly because an anomalous process generated a new distribution produced it. And as a result, then what we want to do is the reason why anomalous pattern detection, I think, is very important because what we often want to do is detect the existence of this anomalous distributions, anomalous process. And one-offs, it's very hard to do that because I can't distinguish between what was just Glenn making a sort of slight change in behavior or was an actual fundamental shift in what's producing the data. And so for me, the whole point is that, well, any singular observation may not look too anomalous on its own. So let's imagine there's a fraudster, but they're not a dumb fraudster. They're very smart. So their job is to, if you think about your distribution as being just simply like really a normal distribution, think about it's normal centered at 0 with some standard deviation. Then if I'm smart, my job is to try to hit transactions that hit right at the mean, right?
Yeah.
Over and over again, because no individual one of those will look too abnormal because it'll look like a very highly dense area or very likely observation. But the idea is that, well, as a fraudster, because I am not you, I'm in somewhat constrained to act different than you. I might buy gas or groceries or clothes, but I might do those things in ways systematically different than how you do it. I might buy clothes that are too large or too small. I might buy gas, but I buy the unleaded and you buy the premium. I might buy locations often that we don't frequent. So all these things,
different time zones and things like that.
Different time zones, right? All these things, like they're similar, but they're somehow a little bit off. And so the point is, if I can find a collection of data that is somehow similar in time and space or in what the actual underlying outputs are, but are systematically kind of shifted off or unexpected in some way, then I can identify the existence of the anomalous pattern versus looking at any one observation that none of them look too off, right? Noise, think about one example I used early in my career when I was first thinking about this question, and it really helped resonate with some of the sort of social scientists I was working with. We're tasked with trying to detect shipments to the country that were contraband. And, in the example of, if someone's bringing in shipments into the country or along some port or along some shipping line that has been known to allow for contraband entrance, let's say it's pineapples, right? I'm shipping pineapples from someplace, but the shipments are all a little elevated in weight, right? Well, the point is that if it was just noise, you'd see some things higher, some things lower, kind of, back and forth, right? If you see systematically error or noise in one direction, right? That's a pattern of something being odd. Your model's off or something's going wrong because noise should be distributed equally across. So one piece of noise, one residual can tell you a whole story, but you see the collection of them in some time or space all above or below sort of the expectation. Well, that's a pattern that tells something odd is going on and worth investigating. So I start with outlier anomaly detection as my framework because I think that helps motivate why anomalous pattern detection is actually a very powerful way to think about what we want to do and why it's important. Does that make sense?
Yeah, it does.
Okay.
I have to admit, my mind tracked a little bit when you said, if you were the fraudster and you were buying different clothes, because obviously I can't help but remember that you're both much better dressed than I am and about a foot taller than I am. So it's like, that one would actually not even be that one would pop up.
That'd probably be very easy.
Yeah.
Yeah.
But yeah, on another note, maybe less important than that example is for example, in the vital signs that I'm used to looking at, where you can actually see, for example, when a vital sign probe is dampened or interfered with in some way, for example, it might actually frequently stick for the average, but the all variation disappears. And so, for example, we'll have, since many of these vital signs, these probes need to be calibrated, and therefore they're actually calibrated towards mean value. So, for example, when you take the COVID temperature test that you've been using all this time, and no matter what, oddly enough, they all shoot up to about 96 to 98 degrees. Like they all hit there, no matter what you're pointing it at. And the fact is, when it hits that variation, even at the average, this is an anomalous data generative process. So no, exactly. I think we definitely agree on what the definitions are for the data generative process. And now the question is so what do you do next?
Right. So then at that point, the framing for the question becomes one of I'll consider optimization, right? So if I have some expectation for what I should see, what I'm looking for are collections of data points that, again, have some self-similarity, but are sort of collectively right, sort of abnormal given the expected distribution. And so what that comes out to being is really sort of leveraging a very rich area of statistics and spatial scan statistics, or scan statistics more broadly, spatial, temporal, or what have you, where we're scanning over subsets of data, space or time or whatever, and trying to isolate some units that sort of form this self-similarity, but collectively are odd. And you can think about trying to find outbreaks of diseases, things like that as a sort of maybe a more canonical example. And so for us, it becomes the data set, the very just general data set of transactions or what have you, becomes this area which we search in. We're trying to find these collections of data records that are collectively anomalous for some subset of their attributes. So it's really a subset scan over records and over dimensions, because you can imagine a situation where, again, if I look at the entire likelihood of the record, likelihood is the product of a bunch of maybe individual likelihoods of each value of the record, or some, depending on if you're taking the logs. And you can imagine a situation where, like, if I'm taking a bunch of products or sums, I could have one or two pieces that are odd, but the collective, other 500 things added all together tells me, oh, this thing is pretty fine. And so you think about, if I take these 5 records and for maybe these 2 attributes, right, those 10 values collectively look weird because they're not if they were random 10 values, they would all kind of move around, but they all collectively move in some odd direction. So that becomes a scanning over sort of records and attributes. And the reason why that's hard is because, scanning over subsets is really computationally expensive.
Yeah.
Right. And also, how do you do it in a way where you still maintain some high power that you reject the null hypothesis that there's nothing going on in this space? And so that's kind of one of the secret sauces that we have, is we basically show in various pieces of work that I have, we show that many of the goodness of statistics that we're used to. So I do things very non-parametric. So I do a lot of empirical distribution, or learn models that are fairly flexible. And a lot of ways we compare non-parametric models is looking at the distributions of things, right? So we might use a Kamal-Gauss-Smirnov test, or Anderson-Darling, Burke-Jones, one of these sort of non-parametric tests, which are looking at empirical distribution 1, theoretical distribution 2, or empirical, and trying to say, are the distributions different or not? And what we show is that a large class of them satisfy some properties that are very helpful, known as linear time subset scanning. And essentially what that means is that I can scan over, even if I have n records, there are going to be 2 to the n possible subsets of records that could be the anomalous ones. But if we sort them in a particularly interesting or purposeful way, so there's a corresponding priority function that's really important. If we do that sorting, we only have to consider a linear number of them. Basically sort them in order, and then kind of greedily go the top 1, the top 2, the top 3, the top 4, all the way to the top n. And we can prove that the subset that maximizes the score, the subset that we find in that linear set, will achieve that same score. So it's not there could be multiple subsets that achieve the optimal score. This is not guaranteeing that you find all of those or any of those. All of those. But what it does guarantee is that the one that maximizes this linear set will achieve the optimal score, whatever that is. And so that lets us actually scan very efficiently, considering only a small number of subsets, but still provably finding the subset of data that are, statistically speaking, the most anomalous. Or another way kind of intuitively to say is has the most amount of evidence that against the null, essentially. That the subset with the most evidence that there's something odd going on. Does that make sense?
Yeah, no, I like that. It does remind me, because, for me, I did like this is one of the first things that popped up when I was looking at your work, is like the fluency that you had between jumping from the statistical to the optimization side. Sure. And I thought the part of me was thinking, is that part of the sort of the heavily like engineering influenced Carnegie Mellon type, it seems like those things can't be. They are not inextricable, or is it? That is, I would say that is not by chance. That's not serendipity. That is actually, I think, by construction, based on how it was taught. I mean, I did my undergrad through my PhD at Carnegie Mellon, so I spent about 9 years there.
And so the most formidable years for arguably for my life, but certainly for how I thought about academia and science and the pursuit of truth and knowledge was shaped, on that campus. And it's so interdisciplinary. So like my advisors were, one of my advisors was Cosmo Lisi, who was a sort of physicist who became a statistician as well, right? Another one is Amelia Haviland, who is a statistician who does healthcare policy and analysis, right? Daniel, who, is sort of more pure computer scientist and machine learning person, but was really driven by solving real world impacts and policy. So not only thinking about machine learning, but also sort of designing systems and thinking about how do I affect policy in a real and tangible way. And so, CMU as a university is very interdisciplinary. And I would argue that the place where I spent most of my time as a graduate student at Hines College was maybe the quintessential example of bringing people together from different disciplines, from OR or operations, research and management, from statistics, from machine learning, from computer science, from information systems, from public policy. We have economists from labor and health economists, all sort of in one room, in one house. And so when thinking about work that was important to me, and when I'm trying to present my work, thinking about going back to that comment you made about presentation, I had to convince not only computer scientists who kind of maybe bought into things, but I had to convince economists. I mean, pure sort of, economists with PhDs in economics from top 10 schools, that what I was doing was relevant to their world as well and had impact in the way they cared about it. And that's hard as a young graduate student trying to figure out yourself what's important. But that sort of, I won't call it a crucible because they tended to be pretty willing to support you. But that environment really taught me to not be beholden to any one discipline or idea, but to really sort of find the places where, here's what I think about this question: how can I borrow from economics? How can I borrow from statistics? How can I borrow from optimization? How can I borrow from machine learning? How can I borrow from OR, OM? How can I borrow from these disciplines? Because we're all speaking, I would say, different languages, but there's some sort of unifying or some kind of, transcendent ideas that are there. And how do we borrow and speak and bridge things? And I think the bridging part is where you see real value created. So that definitely is there. And it's funny because depending on who I talk to, there's some people who say, oh, you're a statistician. And I'm like, not really. I mean, I have friends who are pure statisticians and they would not consider me a statistician. So people say, oh, you're a computer scientist. And I've been friends who are pure computer science. They would say, no, so depending on who you ask, I am that other thing that you're not.
Yeah.
But in a way, like people who are in the other fields, I know statisticians perfectly, easily and speak languages that are similar. And so I like that. It's hard when it comes to defining who you are as a person.
Yeah.
But in terms of actually getting work done and solving problems, I work with people who do information theory, statistics, optimization, computer science, and I do, all of those things. I think hopefully well enough, though I would say most of my work ends up in stats and machine learning journals. If in sort of when it comes down to the final destinations.
Yeah, I was wondering a bit because here's like a very subjective bit that I think that you are good to might be able to help unravel for me a bit. Like when you're deciding, like for example, when you're doing anomaly detection, you're creating this model. You essentially were creating an optimization search regime.
Sure.
Is that fair so far?
That's fair. Yeah,
cool. But you could always say, and one, I'm obviously very sympathetic to that, given that I've done like literally very similar things where I just said like, okay, I have this statistical problem in anomaly detection. I'm literally going to run an optimizer over this, and do it Bayesian non-parametric, Bayes opt over this to try to get something that I want. But back to your work, the alternative is, you could try to create a more complex, purely statistical model to achieve what you wanted. So where is sort of like the trade-off? What works? What doesn't? Did you have any successes or failures? What was going on there?
I guess one thing is definitely my training. And a lot of what I do, and a lot of what I've been able to exploit comes from, the lab and the advisor I had mentioned, Daniel Neal, before. And Seth and I, again, Seth Lackman, for example, and I, paired Daniel as an advisor when we were in graduate school. And so I think a lot of how I think about questions are often governed by that training because I see anomaly detection anywhere. To me, anomaly detection is when a system, and that's very generally defined. It can be like literally a physical system, like the sensor readings on an airplane, or the sensor, or like sort of readings from some device, or a behavioral system, like the transactions you generate with your credit card or things you buy on Amazon. And when a system is deviating away from expected behavior or desired behavior, that's the anomaly detection sort of paradigm to me. And so, and I see that everywhere. I see it in causal inference. I see it in economics. I see it in social science. I see it in policy. And so for me, it becomes a question of, these are the questions that I see and I uniquely see them. How do I frame them in ways that allow us to get at the questions and problems we care about? And so I don't necessarily feel beholden to anomaly detection or modeling things the way I've always done. I often find it as like just the easiest person to do because it's like a tool that I know very well and know how to kind of like in a very quick in a very relatively small period of time comparatively set up structures that can answer questions of interest to me. But I have work, for example, that's unrelated to this, but I have work that's looking at causal inference, specifically peer influence in social networks when you have homophily, right? Has absolutely nothing to do with anomaly detection at all.
Is that one of the ones you do with Cosmos Release?
Yes, yeah. We have it. It's at a minor revision now at JASA, but it's one of those things where it's like that's purely sort of a question because I actually did a lot of anomaly detection in networks as well with a colleague of mine, Skylar Speakman, and Daniel, and Skylar now is a director of machine learning at IBM Africa in Kenya. We do a lot of work together as well. And so I got into networks because of looking for these sort of subgraphs or subnetworks of anomalous sort of activations, and sort of brought me to networks. And then I kind of talking to Cosmo and sort of things, as you know, these things kind of grow, but very much not related to anomaly detection whatsoever, but a really important question in many policy and business questions that we care about. And so I think for me, problems, I'm geared towards solving particular sets of problems, things that I see. That's the Heinz training to me. Like, where's the impact? What's the problem? What's the important thing we can solve? And I'll bring to bear whatever tools I have available to me to address that problem. And as you mentioned earlier, the engineering part, I am not someone who says, oh, I have to do work all the time that, if it doesn't require me to build something new, it's useless. I am perfectly fine with taking things off the shelf that exist already and applying them to problems that are important because the problems being solved are important. What I do often find, though, is that our questions we care about, though there are some similarities in their sort of structure, they're often nuances. And what I think a lot of people who aren't trained the ways sort of we are do is they kind of try to take this and that and kind of staple it together and tape it and try to shoehorn it to make it work. Whereas I think as an engineer at heart, I build what I have to build to solve the problem I want. So if what exists doesn't exist to solve the problem I need, I build the thing I need to solve that problem. And that's where you obviously get nice new novel work, novel algorithms, novel theory or whatever, but I'm not beholden to what I do.
Yeah, no, that is an interesting bit because usually one of the sort of riffing off this idea that one of the ways that I try to approach my work is one, if I can take something off the shelf that works and apply it, great. However, as you said, nuance means that basically nothing off the shelf is going to work. It's practically nothing unless you are literally taking the old data set too. It's and I was actually talking to my supervisor, Steve Roberts now. This is pre-COVID, but and he was he does a huge amount of method development and model development, and he's talking about the challenges where it's you can take this vanilla algorithm, but a massive amount of the effort and a massive amount of the sort of the new innovation about this is how you actually apply it to the nuance of the problem at hand. So even these people who are, extreme experts, and I consider you also an expert in developing model development. I'm not an expert in that, but I'm an expert at sticking things together and not making it go haywire. Like I think that's my special power.
Skill.
Yeah,
that's a very important skill.
But like I do view it as like, putting building blocks together, and the main you can do that. Like you can put different building blocks together to address a new problem. But the challenge is you make sure that you weld them together and that they aren't so completely unprincipled that stuff just starts leaking out the side. So like, and so, I guess I view it like, one, you can build that holistic new model.
Yeah.
Or you can start, welding things together. You don't staple, you don't tape, you weld it together, and it has to be very, very, very tailored. I guess this is one of the reasons why I actually really like, I haven't done too much work with them, but copula modeling seems like it's it's like, it seems like it's the engineering-ist like statistical process that there is, because effectively you're taking these different building blocks and you can do so much tailoring and so much I guess tailoring would be the way for each of those building blocks, and then you build on the next step. And then you build on the next step, and then you can tailor each of those. And I found that really, really interesting. I haven't been able to explore it as much, but do you think where would you sort of see like the breaking points to those? Because I do recognize there are breaking points in the way that I do things, but is it just you have to test and see, or do you have a grander theory?
So honestly, I would like to say I had a grander theory, but I don't think I have one. I think for me, I think a lot up front on the problem about what it is. And I try to really break the problem down into its most basic building blocks. Mm-hmm. And I try to map it to things that I know well, or understand well. And so sometimes that will involve then, mapping it to something, and then, well, does it thing map relatively nicely to that thing?
Mm-hmm. Yeah.
If it does, great. We'll start with that. And then again, like you said, we kind of weld things on top of it and top of it, kind of build up what you need. And it may be sometimes it, sort of the first part maps well to this, second part maps well to this, the third part maps only somewhat well to the other thing. And then because, now is the question that now that I have a kind of, a stable foundation, but like my second story is a little wobbly, am I going to think about, how much structure do I need? Am I building 10 more stories on top of this? Or is it just simply at the end of it?
Yeah.
Okay. And so if I'm building more on top of it, then I'll start to really think about how do I properly build this thing. If that's kind of the end and the real workhorse was at the sort of foundational level, then I'm more willing to sort of like deal with this sort of like maybe not approximate mapping. So I think that's where you get into trouble if you're approximately mapping every story of this thing you're building, then you get these leaks and wobbliness. And that to me is really a judgment call. And I think that's why a lot of statistics, a lot of methods and things we do, machine learning, actually people say, I just think the machine learning sort of, data science or sort of learning algorithms broadly, we pretend like these models and methods are very general, but they often require a lot of training, a lot of ingenuity, a lot of tweaking to make them work, let's say, really well. They're not generally perfect. They work well when I built them for the problem I built them for and tuned them for that. And so I think that that's the part where we're not, maybe we're being a little disingenuous, or maybe not being as honest as we should be about how sensitive these things are that we build to not only just parameters that we say, hyperparameters we say, but just kind of like the way in which the assumptions being made and things that are happening. So I don't have a grand theory. I'm all about sort of practically solving the problem however you have to and however you can. But assuming that the scientists, and I take this approach to myself and hope others do as well, where we're going to be honest about it and really think about what is right. What is the correct way? And if we're not getting the correct way, saying, listen, like, this is what I'm doing. Here is the issues with it. Like, it works fine for me, but like, don't just apply this off the shelf because here are the issues I encounter. We often like to hide those things or, and there's incentive structures in terms of what journals publish that affect those things. But I think as scientists, our job is to find, capital T truth and pursue that. And so hopefully we're being honest when we build these things and talk about what they're doing.
Yeah. It is interesting. The more I've talked to people, the more I found that without knowing it, the people who I really wanted to bring onto the show are also the ones who also really hammer down on the issue of like being a scientist, and that they essentially many of the times they view themselves as a scientist first, and whatever technical skills they need to bring to bear, great. But they're scientists first, and they're just chopping at it that way. What do you think? When it comes to being scientific on these issues, what do you think are sort of like the good critical assessment skills for this? I always like to say that people should be always inductively testing. So essentially, they need to be testing out their ideas. I'm not going to get this right on the first try, but the idea is like they need to make sure that their models aren't like deductively wrong for some reason.
Sure.
So as in like essentially, if the math is straight up wrong, you're probably not going on the right path.
Sure.
Or you should be really, really sure that that's like the last step, as you said. Like if this is my final approximation, but also understand that like a lot of the deductive truths of their models does not actually apply to their data. It's just a truth about what's being fed in. If you did so, like a frequent thing that I've seen is like people actually they use a model and then they use the model's assumptions as a statement about the data that they're putting in.
Yeah.
And so it's like, yeah, that's not quite right. Let's start over and say, here's what we think about the data. Let's make an assumption about the data and then move towards the modeling. But anyway, so what are some of the traps and things that you've noticed?
Well, I mean, those are absolutely correct. I think so. Let me try to. You got my mind working in a couple of different places. So let me try to address the first part, but let me take us in a direction after that I think could be interesting. It's of interest to me. So therefore, I'll take us there. The first part is, I think that you're right that when you build these things, you want to be very careful and thoughtful about not letting what you can do dictate what you do, and what you assume to be like. For the math to work out, we make assumptions X, Y, and Z, and and does that really play out in our data? Well, we're going to assume it does because we're going to, make a regular condition that we can show that this is minimax if it's this, Lipschitz. Like, well, but like, does that make real sense? Now I get that we have to make a lot of theoretical conditions or regular conditions when we're trying to prove things. I've done them myself. I get that part. But I guess the part is like to me, there is a distinction between I am building a model or method or algorithm in theory about it, and I'm building a model, method, or algorithm and its practical uses. And what always governs what I do is the practical use of it. I do publish, I do think about statistics sort of at a theoretical point of view often. And often we need, in order to get papers published or get some sort of visibility, being able to prove sort of general truths about things are good. But, a lot of theorems that I read and write are asymptotic, right? And I have no idea when asymptopia kicks in, right? We have no idea. But unless we get rates, right? Like, I don't know what that means. And so what I want to be able to show always is even if my theory is nice, what I can hopefully show you evidence of in a way that's meaning to be extremely persuasive is it fits the data or the context very well, even when theory hasn't kicked in yet, or even if, even if things aren't Lipschitz, right? Like, here's how it's going to gracefully sort of approach that. So I think it depends on your goals. There are some scientists who really think a lot about theoretical things, and I think there's value there. And I think I do think about theoretic stuff as well, but I also think a lot about practical things. And so I think if you're someone in practice, though, if you're using a method or model in practice, your fundamental goal is to try to recover the data generating process, recover what the data is telling. And I think this is actually something I've thought a lot about. Sort of the thing I want to bring us to is that there's a lot of, so I think anomaly detection is a very powerful lens and framework for a couple of reasons. Because I can frame a lot of questions we care about anomalies. The canonical one, I think, is that the model or the expectation for Glenn, historical Glenn is correct. And current Glenn transactions may in fact have some evidence or some examples of anomalies or things I want to find, right? Interesting things, patterns or whatever, right? And that indicates that maybe, again, fraud or shift in your behavior, maybe you got married or have children. And so, there's some shift in that and I want to find those. So the assumption is that the model is the model or expectation is correct. The data potentially has dirtiness or error in it. We want to find it. I think another question, if we flip what in fact is the right thing, is that situation where the data is right. Like the data is what I observed. I observed, these transactions, or I observed these decisions, right? And now I'm trying to figure out what model governs that. And so I could presuppose I have used this machine learning model. All right, let's very basic. This regression model. I have this linear regression model, and I fit that to this data. And so that's what I'm going to say now impose. Like, the model assumes linearity, additivity, and that's what my data looks like. If it's okay, so that's what I'm going to assume is right. And the question I think is, well, if we think about anomaly detection this way and say, well, the data's right, and the models what I'm trying to could be wrong. I'm trying to figure out is I can then fit models to data, and then ask the data and model questions like, well, are there any systematic anomalies under this model, right? Like, does anything look weird under this model? And if it does, what I've identified is places where my model has been wrong, where I now need to go back and think about how to build a better model. You can think about very canonical, very simple examples. If you have a quadratic and you put a line on it, right? A linear regression, your model is going to be wrong in particular places, right? Yeah. Specifically, sort of maybe toward the middle or toward the end, where you can see this kind of pattern of poor fit, lots of residuals that are maybe underestimated and then kind of overestimated and then kind of underestimated. And so what that means is that your model's not flexible enough. In this dimension, it's missed something. And so I think that there's a whole area of anomaly detection that I've been working on very recently, like the last few months or so, trying to think about this question of can we flip what's right and what's wrong, or what is considered a sort of perfect and what is sort of potentially muddled, and use all these same ideas to begin to investigate, let's say, models now, not just investigate data, and find and build better models, and build better representations of reality. Because I do believe that in the end, it is true that you're not going to probably ever capture data generating process perfectly correct, because especially human behavior is so complex. Yeah. But we can learn enough from them to understand and model them relatively well, because humans are still pattern producing machines, and understand where our models are kind of gone awry, where our assumptions are kind of misleading. Does that make sense? That kind of that frame.
I love that bit. Yeah, because those are actually. It's funny. It's a similar process that I go through when these two things, flipping them back and forth. I had never articulated them in that way. As in, I use different words to articulate a similar thought process that I'm always shuffling back and forth from. So no, I definitely appreciate you sort of bringing some new vocabulary, at least to me, on that issue.
It's what I've been thinking a lot about. I think it has a lot of potential. It's something that it's an area I'm working in right now, and I'm trying to build toward. And it leaks a little bit into things like fairness and bias in models, but also just kind of broadly building, as we're building these very complex neural networks with parameters, and we don't know what the right activation function should be. We don't know what the right, how many layers we need. We don't know, all these things we don't know things about. Can we begin to have systematic procedures that will identify and highlight for us this information by saying, well, the data is the data. This is the right data. How do I then build a model to capture that data? And is my model flexible enough, or is it missing something? And where, if it is, where is it missing something?
Do you, just out of curiosity, if you don't mind me just shooting something out there, and if it doesn't make sense, that's fine. Do you think that, so one way that we could do this is, you create a model and you look at for residuals, which is essentially you look at the data itself and see where it fails to fit.
Yeah.
But also wondering, given, now at this point we have tensor libraries and everything like that.
Yeah.
To what extent can we sort of look at the model fitting process, or the tensors, or the change in likelihood with these models? Are those providing new pieces of evidence that we can start piecing together, or is that weird?
No, I think you're right, and it's something again I've been thinking a lot about. This is something I thought about with concert with Skylar in his lab at IBM in Africa. But I think you're onto something. This is something that I think is very important. So let me say it in this way, and tell me this connects to what you're thinking about. But let's use deep learning because it's a very hot topic these days. And one sort of way we've thought about sort of building models is things with like GANs, these adversarial networks, where basically we have a model that's trying to learn, that's trying to generate basically something that looks at the data, and some other model which is basically sort of deciding, okay, well, can I distinguish between what is generated and what is true, what is really from this data process, right? So if the model, the sort of generator gets good enough at generating fake images or fake pieces of data, if it's captured data in the process very well, then it would have done it to a point where it can fool this very powerful discriminator, which can decide between what is generative and what is not, right? So this adversarial sort of setup makes sense. It's a great framework, in my opinion, for thinking about these things. But often what we're doing is we're, and I don't have an answer to this. This is something I'm thinking actively about.
Yeah, we can just go all dialectic on this and just see how far we get. Yeah, that's cool.
So like what we're doing is we're basically saying, okay, like, did I think, here's an example I generated. Okay, was it yes or no? And it says, okay, this was yes. I can tell you that this is a fake one. And then you basically back propagate information about kind of, okay, here is, this was clearly a mistake. Let's update our weights, update our model in a way to make sure that we can maybe not make this mistake again. That's clearly, valuable. But again, there's information in this, both in terms of, I think, not just is it real or not, but understanding why, right? Like what pieces, what pixels, what components, what facets of this were clearly the problem. And secondly, when I update my information, I really don't back up. I mean, like, there's only a certain set of things that are getting updated and informed, right? This was a problem because some subset of my nodes or activations were off. And as a result, could I actually be smart about not only updating things intelligently, because only some things actually need to be updated or thought about, but actually propagating not just yes or no, but like, and it's because this subset of information was a problem backwards, right? And so this idea makes sense even in, take a linear regression, and we're trying to fit a curve to it. Right. And I'm going to say like, okay, like, here's my prediction, here's my error, whatever. And it's okay, well, like, you have some pattern of behavior weird over here. Maybe I try to shift and fix it, right? Like, okay, like have my curve, have my line. All right, let me fix that. The problem is that if it's truly a polynomial and you're putting a line to it, you shift it one way, you fix that problem, you have a whole other set of problems. Yeah. Shift it back, set of problems, right? And so at some point, you can't solve the problem because you don't have enough degrees of freedom, enough complexity, right? And so can we propagate information back in a way to this model building such that the model then realizes, oh, okay, the problem is not that like I'm making mistakes because I don't have the right weight. It's because my complexity is too small. Right. I need a first degree, second degree, third degree. First degree by definition is a progression, second, third degree, whatever, polynomial to capture the information, right? So can we actually have the same idea, but like not just by classifying yes or no, it was wrong or right, or yes or no, this was definitely generated by something or not, but actually propagating back information like, oh, and here is the reason why. It's this subset of dimensions. It's this subset of data. It's the black males in your data that you're not properly modeling. Because that, to me, it's helpful for us to know, right? As we're thinking about things. But if we can actually figure out a way to propagate that back to a model itself, then we can begin to actually have these models sort of flexibly figure these things out in some nice way. And it has, again, feelings of like boosting a little bit as well, probably, if you're hearing this. Like, there are things that I think try to do this, but not in the sort of pattern of anomalies way that I'm thinking about them. Again, the point is I have no concrete way of thinking about it yet. This is actively what I'm working on, thinking about, pushing forward. And hopefully might be a part of my research stream in the next 2 years, is thinking about how to take anomaly detection to model building, to bias, both in terms of like sort of like fairness, but bias also like just bias in our estimation of data.
Yeah, no, that is cool, and I appreciate you being brave enough just to like walk through your string of thoughts, because honestly, that is interesting. I think that actually walking through your thoughts on that, I actually have a clear idea of what you're actually trying to deal with. A similar idea that I've been sort of playing around with is it's sort of, I'm not going to say decision theory because it not have
Okay.
much to do with this, but like the idea that for example, if when I'll just say, make it very general. If I give you two pieces of advice, there's a river and you can go over bridge A or bridge B. And what you don't, and these two bridges are separated, so there's a key factor.
Okay.
You can go over either bridge in order to achieve your goal of crossing the river.
Right.
What you don't want to do, though, is take, of course, the average of two bridges because you will end up in the river. And so one of the things I've been thinking about is like from a modeling perspective and anomaly detection, because it comes back to this idea, like, do I believe, like, is the data right? Is the model right? What's playing around here? And which one am I to believe is my truth, by which I'll then detect anomalies.
Right.
And basically the idea is that essentially I'm trying to play around with the idea of proposing two very like different models to the data and effectively how to parse through that information. So you might say, just to keep it simple, that we might have a linear data set, and we have a quadratic data set, quadratic relationship. And it's like, we might know it's one of those, but we don't know which. And so effectively, it's the idea that we're going to propose these two different models and then effectively have to decide which one it is, and then make our inference based on those.
So just to understand the question, so in the data, we're modeling some outcome Y, the function of inputs X, and you're saying for some subset of the X's, Y is a linear function of it.
Yes.
Truthfully, and for some subset of the X's, Y is truthfully as a sort of a quadratic function.
Yeah. So basically, and those are what I believe the data generating functions are. So one of these data generating functions is truthfully different than the other, but our data is mixed.
Okay.
And so basically,
I see.
Yeah. And so I guess what I was trying to think of is, there's plenty of ways that you can test that. You can just start comparing, you can try fitting things like that. But I guess the issue that I was interested in is, as the data becomes more and more mixed, is one thing where, for some of my previous work, like patients, where each patient is their own thing, and therefore I can personalize it. And therefore I can test both out, reject one, and proceed on with my happy self. But in some of these other scenarios where they are truly mixed, and I was just like, this isn't a well-baked thought, but it is one of those things where I'm just trying to think, like, is there, what at least would be like a good first order way? And that's one of the things I like to talk to smart people about, because even if they have like a quick gut feeling, it might lead somewhere, even if it's not the quite right answer. But like, is it sort of a divide and conquer approach where I try to propose two models and compare, or how would you approach a problem like that?
A really good question. It's a tough question. I've never thought about it before. I guess my gut on this, I have an idea, then I think about what kind of why. Yeah, I do have a tendency to do this, and I do this with my students often, because it happened to me. Sort of side story why I'm going to sort of talk out loud how I think. Mm-hmm. I had in grad school, I had algorithms class as a PhD student. And the professor of the class was Manuel Bolon, who you may not know, but he's a Turing Award winner. He's a brilliant mind. And he did some work in security. So a mathematician / computer scientist, he sort of won a Turing Award for his work. And the best class I ever had in algorithm was his class, because he would come in and say, like, here's a question. Like, we're going to try to talk about splay trees. I don't know, whatever. Like, I don't know how they work though. Can like someone explain them to me? And he would like, or he'd be like, oh, let's look at, he just like kind of walk through with somebody else kind of what he's thinking. Mm-hmm. And so while I might not understood a lot of it, I got to see how his brain worked and what he got caught up on and why. So I found that very helpful as a learner. And so I do that a lot now with people. And so that's why, again, I walk through my logical fork. I have no idea what I'm going to do, but here's what I'm thinking. Mm-hmm. Maybe that's helpful. Maybe someone will feed into this and solve this problem and answer it for me, which is great. So in this question, you've posed to me, I don't have a good answer, but my logic is, well, okay, so there's going to be some subset of people, like, so in your argument, there are data points that are truly linear, sort of data points that are truly quadratic, and data points that are potentially some mix. And so the easy part to me is, well, find the people who fit the one of the things, right? And so I can do something simple as like, all right, I'm going to either sort of, I can do Bayesian where I have priors of both these and kind of figure out posteriorly which one you sort of maximizes the posterior probability.
Mm-hmm.
I can do detection where I use, I sort of have, I sort of say, here's my expectation based on the linear, expectation based on the quadratic, and then find people who are anomalous given the expectations. And so, boom, you pull them out immediately. So if you're anomalous under the linear, then you must be either a quadratic or a mix, and vice versa. And so, like, you can do these in different ways, but the idea kind of canonically for me is like, how do I get the people who are like obviously one or the other, or whatever, out, detected, separated, picked out. And then the mix becomes a challenge, right? Because my suspicion is that it's not going to be like this, like perfectly, your 50%, like you take your outcome, 50% of linear, and then put another 50% of the quadratic one and then kind of average them together. So it's going to be some weird functional form. And that's the part where I'm not quite sure what to do, because to me, like, the answer is that they're both right, but they're also both wrong, because the true answer is some joint of them. And I'm not sure what that functional form of the joint of them looks like.
Right.
So that's the part I don't really have a good answer for. I mean, I can imagine, again, my first view is, well, I have anomaly detection as one option. So if you don't look too anomalous under the linear, but you fall into the mix, well, then I'll kind of say, well, like, you're mixed, but like you're dominated by the linear one. Or maybe vice versa for the quadratic one. But again, that just helps me get down to like the other group that is like anomalous under both or whatever. And then I don't know. I mean, I guess the answer is philosophically, it's both and neither. So I don't actually know. It's a good question though.
Yeah, no, it is interesting. And I enjoyed just you talking there, because the sort of the divide and conquer approach I was saying is like, take what I can easily figure out. Put those aside. And now those aren't my problem anymore. And then it's like, okay, now what's the next set? It's like, okay, here's the mix. It's like, oh man, these ones are a real problem. But yeah, cool. Are we running close on your time, or how much do we have?
I've probably another 7 to 10 minutes.
Cool.
If you have, we can sort of begin to wrap up if you want, but happy to take another 10 minutes with you.
Perfect. Yeah, I wouldn't mind. Something that one thing that I'm interested in is you move fluidly between different subject matters in a way that I think is very cohesive. Yeah. Okay. It looks good from the outside.
Okay. Good.
Yeah. But one thing that I've noticed is that it seems like a lot of people who are early in their technical careers seem to be much more towards the issue of siloing some of these techniques. And so, for example, just as a quick example, I was talking to a group of people in machine learning. So they do statistical machine learning. Okay. And I was going to give them a presentation on Bayesian optimization. So just let them through it and just ask them, it's like, okay, well, who's done solved an optimization problem before? And only the group lead raised the hand. And it was like, so here's the thing. It's like, has anyone solved a linear regression problem?
That's an optimization problem.
That's an optimization problem. Like, and so it's interesting to me. And I didn't do this to be a jerk. Like, I don't want to be the guy who quizzes people during those things. Like, you don't be that guy. Whatever, any guy you want to be, don't be that guy. But at the same time, like, I feel like I would be failing people in some extent to just realize, like, wait, real quickly, let's say something here. We have OLS. There's an analytic solution to this optimization problem. If it's too big, if the computation is too big for the analytic solution, we have an analytic solution to the gradients, which allows us to then solve it because it's convex. And okay, cool. Yep. And now for logistic regression, we have an analytic solution to the gradients. We don't have an analytic solution to the actual solution. We plug and chug. And then, for example, Bayesian optimization, what do we have? Well, we actually have an analytic solution to the gradient. However, it's a non-convex problem. Yeah. And so we can go from there. But, you get the idea. And by that, I mean, there's an analytic solution to the gradient of the Gaussian process model that we're trying to fit. So the likelihood. So before someone complains at me in the comment section. But but the idea here is But the idea here is that people were separating these things, like, I think far too much than they thought. And I know some people just like, I don't want to say more than I know or something like that. But What are good ways? Is it just the practice where you just practice and solve problems and you start pulling these things together, or have you found anything?
I think you're onto something here. And again, I don't want to. Again, I too try to be as precise about what I do and don't do, or know and don't know very well, because I don't overstep my bounds. And I give all deference to people who are far superior and far more knowledgeable than me in each one of these individual areas. So there are people who who I look up to in statistical machine learning, like and I would never sort of say, oh, if they say something and I might disagree or whatever, that they're wrong. But I think about this all as, I don't know, like math, stats, like problem solving in some way. I guess I don't have the right sort of like discipline specific definition. I know some people be very sensitive about, well, machine learning is different than statistics. And people say, no, it's just statistics, but rebranded. And I don't really wade into those battles or wars, honestly, because I leverage all those tools. But I think I don't have an answer of how to build it. I can tell you why I think I built it. And it goes back to what I said before, is that I never came at this as, I'm a computer scientist, let me do computer science. I came at this as, there is a fundamental question or problem we want to solve. Let me come at it as a scientist and use the tools I know, probably primarily, and then other things I might learn to solve them. I mean, if you remember, my sort of at Heinz is the Heinz College, where I sort of primarily sat as a graduate student, like is a school of public policy and information systems. Or I should say, the Heinz College has a school of information systems and management, public policy management, which relates to basically people who study IS and IT, and people who much more and more economically focused, who study policy decisions in these contexts. And I sit in a business school right now. Actually, I guess I'm actually leaving the University of Minnesota.
Oh,
I'm actually joining the Harvard Business School in July.
Oh, congrats.
So yeah, thanks. Yeah, I'm really excited about the Technology Operations Management Unit. So I'll start that in July. But my entire sort of academic career, even post-graduate school, have sat in business schools, right? And so in order to think about those questions, which are big, important questions, which impact, organizations, policy, government, all these things, and sometimes abstract them, you have to be well-versed in thinking about and structuring not unstructured necessarily technical problems, right? But unstructured like verbal processes or policy or business problems. And so I think if you chase after, I was always very passionate about making an impact in the world around me based on how I grew up and what was important to me. And I was never beholden to my discipline or my title or whatever. Again, the challenge of that is that if you ask, like, I'm not saying this is my aspiration, but I'm not like famous or well known, I think, in any particular sort of like, main discipline. I would even argue that even in Anomaly section, so I think that's probably where I'm most known. If anything, I'm not sort of a flagship brand name. But I feel like whenever anyone talks to me and I talk about the work I care about, the work I do, and the little papers I do write, I think can be considered very engaging because I'm thinking about those things. Often I get from reviewers, my issues are, you spend, I have a paper, sort of an R&R, JMLR right now. And one of the responses we got back, which was honestly not incorrect, was you spend 2-3 pages building up this story about this thing, right? I write for the reader. I write for somebody who wants to understand the problem. And you could just say, well, cite a paper and say, okay, here's the problem context. Like, define it mathematically, cite some papers and be done, and do that in 2 sentences. Where I help you see the tensions and the problems. And so I think when you start thinking about the problem, not the math, but the actual underlying problem and the tensions and the challenges, then I think what that gives you is practice flexing that muscle. So you can begin to translate from, social science questions, business questions, policy questions, technical questions, statistics questions, machine learning questions, and sort of see the thread that persists across them and kind of say, okay, this is an example of this problem. Here's how I can translate this question of fitting a model. When I talk to an OR person, it's just, something maybe a linear program or a quadratic program. At a session is just sort of, maximizing some likelihood, or, I'm just trying to sort of, again, optimize some objective function in the statistical sense, right? Like it sort of like, it becomes these are all kind of sort of on the same thread or band, and we just sort of present them or interpret them or explain them in different ways depending on my audience. So I've given the same talk to vastly different audiences and have both audiences, both technical ones and maybe more applied ones or policy related or business related ones, appreciate what I'm doing because I speak to them in a way that I think communicates, it speaks to the tensions and the problems that they appreciate. And I think that's the goal.
Mm-hmm.
Does that make sense?
Yeah, no, I like that a lot. Actually, it reminds me of one time I was called into the Master of St. Cross College, back at Oxford, and because basically they give you money to go and present something at some conference, and then they basically say, okay, come back and justify like what you're doing, like tell us what you actually are up to, and she basically said at the end, so I showed her my work, because it has all the videos of the Gaussian process being.
I love the videos. I remember when we first met, the videos were very compelling.
Yeah, it's my only way to make friends at these things. But she's like, at the end, she's like, I really, when I saw your presentation title, I was really not looking forward to this like meeting, but I really enjoyed that. But it's like, because again, you build the motivation, the why, the so what, so much, and people are much more willing to go farther with you technical. Like when you don't smack people down technically because you gauge the audience's technical ability and you measure it, but people are willing to take that one extra technical step if they give a crap about what you're doing. And just explaining that, like, it doesn't have to be exactly what they're doing. But I really appreciate that example. Excited to hear about you going to Harvard. We will have a live podcast sometime. I'm going to go up to New England this fall, and
or are you going to be in New England this fall?
Yeah. Because I've missed the leaves for several years now, and so I'm going to go. I'm just going to knock out go Connecticut. I'll swing through Boston, and we'll do live podcasts. We'll look at leaves, and
when you get to New England, definitely connect with me. Send me an email. We can connect and have another conversation if you want. I enjoy these things. Obviously, I do it for a living, so I'm happy to talk more about it. Also we can actually have a beer and chit chat just about life as well. Sort of off the record.
Off the record, sounds good. Well, Ed, thanks so much today. I appreciate your time, and I really enjoyed what you said.
Yeah, I appreciate it so much. Thanks for having me.
Hey guys, it's Glenn. Thanks for your time today. I hope you liked today's episode. If you did, please consider smashing that like button. It's the single, simplest, fastest way to make sure that YouTube shows this video to more people. If you really want to go crazy, consider subscribing or going to our website and joining the mail list. If you want to go totally crazy beyond that, forward this to a friend or colleague who you think might enjoy this too. We're a small channel and every bit helps. Our next episode will be coming out next week, so in the meantime, feel free to look around the channel and see other videos that might be of interest. As a quick disclaimer, the views expressed on the show do not represent anything other than the people saying those words, views, etc. like that. It doesn't mean anything about their employers or their employers' views or some thing about their employers or their neighbor's cat or anyone else not saying the words. And in fact, given that people tend to change their views when they're thoughtful enough, it might not even represent the views of the speaker by the time you're hearing the episode. So definitely come back and see if they've changed their views at a later date. They also don't represent the views of our sponsors. Thank you to our sponsors. You can check them out on our website.